Good morning, everyone. So, in this presentation, I would like to explain you about the another part of the mechanical system. That is nothing but in this presentation we will see how the mechanical system with torque as input is converted into the equivalent torque voltage analogy, and similarly by applying the torque current analogy we will convert the given mechanical system into equivalent electrical circuit. So in this today's presentation I would like to solve one important example for you. Let us go into the subject actually. In today's presentation, it is our lecture number 48, in which I am going to explain you the mechanical rotational system, which is basically under mechanical system. And in previous presentations, we have seen mechanical translational system. Today, we will see the mechanical rotational system. Okay, so which is very important, especially in academic point of view. It is more helpful and useful for the college going students of BTECs, especially exclusively. Therefore, in this particular system or in this particular mechanical system, what we are going to do is that for any given mechanical rotational system, we need to find out the equivalent electrical circuit. That's what our objective is. That so in this your mechanical system will be given in the examination and you will be asked to draw the electrical equivalent part of this, right? So okay, before going to that, what are the basic elements that are associated with mechanical rotational systems that we must know first before going to convert the mechanical rotational system into electrical equivalent part. We must know that what are the elements associated with mechanical rotational. Nice. In previous presentations we have seen mechanical translational system. Translational systems means that it is you can shift from one place to another place. The system of mechanical nature which is having so many mechanical elements like some mass element, okay, some frictional element and some spring constant and a damper element. All these elements we have seen in mechanical translational. Okay, in this rotational means the system which rotates, like your motor, let us say DC generator, motors, even the fan. These are the things which comes under this category. Rotational means it rotates, rotating part will be there. And for that mechanical system, okay, for that mechanical rotational system, how we can represent the corresponding equivalent electrical circuit, right? Good. Now, so in this mechanical rotational system, what are the mechanical elements that are associated? So basically, here also we have various mechanical elements like mass element. The first one is mass element, that is denoted by mass element, and the mass of this mechanical element is represented by the moment of inertia J. J is the moment of inertia. And second is the another mechanical is obviously your dash part. Basically this is represented by like this. This is dash part, capital B, or sometimes called as damper factor, frictional coefficient factor, like that. And second is the spring constant. Obviously, as we have seen, this is K. This is your spring constant. And similarly, theta. Theta is the angular displacement. Theta is the angular displacement. These are the basic elements. First element is, this is mass element. Okay, the mass or the weight of that mechanical element is represented by J. What is J? It is moment of inertia. And second is the your frictional coefficient or damper coefficient B, or sometimes called as dash pot. And the third one is spring constant K, and the fourth one is the displacement, angular displacement. And there is fifth one is also there, that is called torque. That is called torque, that is denoted by capital T. These are the mechanical elements which are associated with this rotational system. And then how these mechanical elements are converted to electrical equivalent circuit. That is what the question, using two kinds of analogies. As we have seen previously, here also in this mechanical rotational system, you will be asked to convert the electrical equivalent using torque voltage analogy. What? Torque voltage analogy. And then the second one is torque current analogy. Torque current analogy. Previously we have seen in mechanical translational as force voltage analogy and force current analogy, that is there, that is applicable for mechanical translational. Whereas coming to the mechanical rotational system, in rotational, instead of force you will be using torque, right? Torque. So here torque will come instead of force, right? Therefore torque voltage analogy and then torque current analogy. Using these two types of analogies, we can represent the given mechanical rotational system into corresponding equivalent electrical circuit. And one important thing that I would like to bring to your notice is that, so if you recall our previous presentations on mechanical translational system, there we have used the same force voltage analogy. So in previous case, what is the method we have used and how the mechanical elements converted to the corresponding equivalent element? 99% same as the same equation, same procedure of force voltage analogy of mechanical translation is exactly equal to torque voltage analogy for this rotational system. Understood? So the force voltage analogy of mechanical translational is exactly equal to torque voltage analogy of rotational system, and the force current analogy of mechanical translational system is exactly equal to the torque current analogy of this rotational system. Almost all equal. Okay, so the mechanical translational system, whatever we have procedure followed for that voltage, force voltage analogy is same as here torque voltage analogy of this rotational, and that force current equal to here your torque current. Only the difference is that, the basic difference is that we have f of t there, here we have torque. In mechanical translational we have f of t, whereas in mechanical rotational instead of f of t you will have torque t. And in mechanical translational system you have your displacement as x, either x you had as well as y, like that. These are the displacements we have used. To represent the displacement we have used the letters small x or small y, whereas in mechanical rotational system we will use the the displacement as theta. And then the mass element, there we have used m to represent the weight of that mass element, the letter m we have used, whereas the moment of inertia. And b and k, all these are almost all same. Therefore instead of m you have j here, and instead of x there you have theta here. Instead instead of force there you have torque here. Clear. Therefore these are what the simple differences. Now quickly I will explain you one example so that you will understand better way. Okay, I will consider one mechanical rotational system example, and I will convert that particular mechanical system into electrical equivalent, and definitely you will enjoy this. Clear? So I will draw the circuit, mechanical diagram, and I will convert that into electrical equivalent part using both force voltage as well as your torque voltage and torque current. Let us consider the block diagram. This is one example and very important also. Let us consider this particular mechanical rotational system. It has moment of inertia as J1, and this is connected with a spring to another mechanical system, mechanical block of having moment of inertia as J2, and the here it has this kind of, this is what your torque T is there. Angular displacement with respect to J1 is your theta. Clear? This is the common element between J1 and J2, that is denoted by K, and this J is connected to one dash pot element. Actually in the problem it is given as F, nothing wrong, you can consider it as B also. As it is given F as in problem, I will also consider it F only, and your angular displacement here is given as theta 1. Okay, this is the theta 1. Clear? Theta 1, let us say whatever it is, you can call it as, for our simplicity I am writing for you that you can consider as theta 1. Why? Because J1 is given and it is J2, then you can consider it as theta 2 for more convenient, right? This is your mechanical rotational system. This is the example for a mechanical rotational system. So now my target is to convert this particular mechanical rotational system into electrical equivalent part using torque voltage analogy. Now I am applying using torque voltage analogy. So using your torque voltage analogy, you must know that first how the torque will be converted. T, how the torque will be converted. So in torque voltage analogy, your torque is converted into voltage, because torque to voltage you are converting. Therefore your torque will be converted to voltage of electrical. This is mechanical in nature and voltage is the electrical part. So T is converted into your voltage. Similarly, J1, moment of inertia of J1. Normally J in general, but 1 is given first block, that's why I am taking as J1. So in your torque voltage analogy, how the mass is, how what element we have considered in force voltage analogy there, your M equal to L. Similarly here also J1 is nothing but L1 only, because okay, whatever we have considered there, same here also. J1, here J1 considered to be as inductance of electrical, and similarly what else is there? K is their common element. Your K is common element. There we have considered it as 1 by C. Here also K by is equal to 1 by C only in this also. Similarly, what else is there? Theta 1. So here if you consider theta is equal to angular displacement, that is corresponding to phi, actually electrical flux, that is called flux. Say it is theta 1 is equal to phi 1, and d theta 1 by dt is equal to, as theta 1 is equal to phi 1, d theta 1 by nothing but d phi 1 by dt, no? And furtherly this is called as your, what is this? V. This is also called as V. These are what, similarly here also the same conversion is applicable for this also. Here also if you take J2, this J2 will be considered as your L2, inductance, moment of inertia converted into inductances, and B here B is there, F or B you can consider. As F is given in the problem, better you also consider, we also consider F. F is nothing but our resistance. F is, okay, I will write for your this thing, this F converted as resistance. Okay, and theta 2 is equal to same as phi 2, like that. These are what the conversions. Okay, then firstly what we need to do is that you write the differential equations with respect to these two blocks first. You need to write the differential equations first. Okay, I will arrange for this and just see how the differential equation part we must write. With respect to the first block, I will direct write the differential equation. So with respect to block J1 I am writing how it will be J1 into d square theta 1 by dt square, same as plus what is next is k. K is the common factor. It is k is equal to, it is theta 1 minus theta 2, theta 1 minus it is theta 2 displacement is equal to, that's all, because there is no damper coefficient here. This is angular displacement actually. So k is equal to theta 1 minus theta 2 is equal to what? Your torque. This is what your equation number 1. You can put in a box and you can call it as equation number 1. You can call it as equation number 1. Clear? This is equation number 1. And similarly, if you write the differential equation, this is called the differential equation with respect to block J1. And if you write the differential equation with respect to J2, that becomes like this: J2 into what is the displacement? D2, I mean theta 2, then d square theta, okay, theta 2 by dt square, plus here damper factor is there, F is there, so it is F into, if F is there for damper coefficient, first derivative of displacement should come, that is d by d theta by dt, plus what common element is there, plus common element, that is k into what is here displacement, theta 2 minus theta 1, theta 2 minus theta 1 equal to 0. So you can put in a box. This is what your equation number 2. This is what your equation number 2 means. This is the differential equation with respect to block 2. Right? Now our job is almost all over. Now we don't need this block diagram now, because we have to derive, we have to obtain the differential equations from this block. Then almost all this block now not required. You can erase this. Now with the help of these two equations, you can write the electrical equivalent equations. These are the equations with respect to your mechanical blocks. So using force voltage analogy, now I am writing using force voltage analogy how these equations will be modified or converted into electrical. So from the first equation, already I explained that your d square theta 1 by dt square will be converted. This can be written as, clearly you must know that how this can be converted into electrical. That's why d square theta 1 by dt square can be written as d by dt of d theta 1 by dt, like this. You can take the d by dt of d theta 1 by dt, means first theta 1 is there, for that you need to derivative, means d theta 1 by dt you must calculate. For that if you apply another d by dt, then that is nothing but d square, d into d square, that is what this, d square theta 1 by dt square. Clear? This further is equal to d by dt of what is d theta 1 by dt? Nothing but your v or v1 you can say. This is equal to d v1 by dt. Clear? Clear? Because here as we are considering your force to voltage, here in this Actually it is same as your current only. It is I1. So there I have explained that I think theta 1 is equal to Q. Same here also. So that is in force current you must use that. Here theta 1 is equal to Q definitely. Okay, theta 1 is equal to Q definitely. Theta 1 is equal to Q definitely in force voltage, and it is d theta 1 by dt is nothing but dq by dt, and furtherly I. So it is di actually. Okay, di actually. So it is di1, because L is there actually. It is finally you are converting J1 as L, no? So it is torque to voltage basically. Torque to voltage means V is equal to again IR form, that we must remember. I into R means we must know that voltage across each element. So your J1 becomes as L inductance, this your K becomes as capacitance. Clear? If J1 is converted as L inductance, and what is the current flowing through that? L into di by dt. Okay, L into di by dt. So sorry for that. I think okay, you can correct it. It is di1 by dt. Therefore, it is di1 by dt actually. di1 by dt you can call it as di1 by dt. Clear? So therefore L1 di1 by dt. Clear? That's what. Therefore you can write this directly. I can write okay, you recall from your translational system concept the same. So means that here you can write this L1 into di1 by dt. Clear? Plus it is 1 by C. What is the voltage? Integral of it is what is the voltage? I1 minus I2. It is I1 minus I2 into dt plus what is your torque? Torque is equal to Vt, voltage V of t you can write. So this is what your third equation using our torque voltage analysis. Clear? Similarly, from this second equation, then how it is? L2 into, it is definitely di2 by dt definitely, plus your F is nothing but B, nothing but your R into what is that? I2 actually. I2. I think I told you that V, no, it's I, current. R into I2 plus 1 by C, okay, integral over, it is I2 minus I1 into dt. Clear? So you can put this another box. Clear? You can call it as equation number 4. These are the electrical equivalent equations for these two mechanical equations. Now, with the help of these two expressions, you can write the electrical equivalent circuit. With the help of these two, you can write electrical equivalent circuit. How it could be, how it look like. Clear? So definitely what you will have, there is a common element 1 by C, capacitance is there common. Okay, so there is two loops obviously, because two blocks are there. So therefore, as you have two blocks, two loops will be there. It is something like this. If you draw the equivalent circuit, V of t is there now obviously. This is your V of t basically. Okay, at the first loop, L1, you have L1. Clear? And then you have common element. So means that you have this capacitance as this common. Okay, and then if you come to the second part, this is the first loop actually. In this you have your current as I1, let us say C is the common element. Come to the second part of L2 and R2, means you can write, no problem, you can write R as per our notation, basically RLC we will write, no? You can write it is R basically, and then L2. This is what your L2 means, this particular L into D. 1 by C. 1 by C, this common is nothing but this element only. Then you can close this, and you can draw like this, and this current is I2. This is what the electrical equivalent circuit of this given mechanical system. Clear? This is what using your force voltage analogy. This is what using your torque voltage analogy. Torque voltage analogy. Torque voltage analogy. This is what the electrical equivalent circuit. Clear? Clear? And similarly, this is what according to your torque voltage analogy. Now, coming to the torque current analogy. If you draw the torque current analogy, how it could be, how it look like. This is again simple. If you recall your those two expressions, differential expressions, from those differential equations, I can write the electrical equivalent part or otherwise. Okay, I think it is clear. Now coming to, I am erasing this. Clear? This is what finally your answer. This is what your answer using torque voltage analogy. This is electrical equivalent circuit. This is answer from these two equations. So L1 into di1 dt means L1 into di1 by dt voltage is equal to 1 by C integral of this is I1 minus I2 and is equal to V of t. Clear from first circuit and from first equation. Similarly, for this, if you write the expression, this is the answer for that. Clear? Now, I will explain you what is, torque current analogy. Torque current analogy also exactly similar to the process or procedure what we have done in previous slide in mechanical translational system. Okay, for your quick reference, I can just rewrite again your expressions, basically those two expressions. What are those? What are those? So it is your first expression is that normally J1 into first expression I will write for you. It is J1 into d square theta 1 by dt square plus it is k into theta 1 minus theta 2 is equal to your torque. Is it not? This is your first expression. Similarly, what is the second expression? J2 into d square theta 2 by dt square plus again k is obviously there, theta 2 minus theta 1 plus f is there, d theta by dt equal to 0. These are the two differential equations what we have noted down from that given mechanical system. Now correspondingly you have to write the electrical using your torque current. So it is torque to current analogy. Torque to current analogy, remember that. So this J1 will be converted as your capacitance. Capacitance. The same we have done in force current analogy of your mechanical translational. So there also the mass is converted into capacitance. Therefore here J1 converted as your C1 capacitance. C1 into it is dV1 by dt. Because it is torque current. Therefore I is equal to V by R. I is equal to V by R. I is equal to V by R form. So it is K is equal to, there we have seen that 1 by C, where in this force current, torque current you will have 1 by L into integral of, what is this? V1 minus V2 into current I of t. Actually into dt also you can write, because as integration is there, really speaking, into dt is equal to I of t. This is what your corresponding equivalent electrical circuit, electrical equation. Similarly for this, you can have C2 into, it is dV2 by dt, clear, plus k is nothing but again 1 by L, integral over theta 2 becomes V2 minus V1 into dt, plus it is F is equal to, here it comes 1 by R basically in torque current, it comes 1 by R into, what is this actually? It is V. It is V. V by R equal to 0. This is what electrical equivalent equations for this mechanical. Okay. So these are the equivalent. Now by using these two electrical equivalent circuits, equations, you draw the circuit. You draw the electrical equivalent circuit by using these two equations. Okay. Now by using those two equations, you can draw the electrical equivalent as like this. It is C1 obviously. So in torque current, remember that you have some nodal voltages like that. Remember that it is V1, let us say, you can have some V2 like that. So at particular node 1, what are the, with respect to V1, we have C1. Identify your C1 as, represent C1 as like this. And 1 by L is common. Definitely that common you have to represent inductance as like this. This is L obviously. Okay. And there, here you can say your I of t here is there. This you can write arrow mark. This is what your I of t basically with respect to your first expression. And with respect to the second, in second V2, C2 is there. Then you C2 you can write like this. C2, and then 1 by L. 1 by L is nothing but common element. Inductance is common, nothing but already we have mentioned here. 1 by R. 1 by R is nothing but simply you draw the parallel resistance. Parallel, and then you join all this. You join all this, and you can draw either reference are not required to show this, ground also not required. This is the basic circuit if you see. This is the basic circuit. So this is what using your okay. Force current, torque current analogy. Therefore, if you consider at node V1 and if you write the expression exactly C1 into dV1 by dt, what is this? I of t is equal to. Similarly, here. So it is nothing but it is integral of V1 minus V2. Difference of these two voltage across this, that is what the current. Similarly, here also R into 1 by R into, so what you can write actually V2, no? This is V2 basically, therefore you have to write V2 here. So here again V2, it is L is there, V2 minus V1 and C2 dV dt. This is what the parallel circuit, it comes like this. This is what using your torque current analogy. The same principle, whatever the problem comes actually, it may be simple problem or complex problem, whatever it is, the concept is like this only. You have to solve like this. So means what we should remember is that, so what are the, how the mechanical elements can be represented with corresponding their equivalent electrical parameter, that we should remember, and from that we need to draw the electrical equivalent part. Clear? I think you have understood this and you have enjoyed this particular. Okay, let us finish off this presentation here, and we will continue with some more questions, especially from GATE as well as IES examination questions on these topics. We'll see in the subsequent presentations. Okay, thank you one and all.